Okay, so in the last lecture, we have went through the some fundamental introductions about the stress and strain analysis for the flexible pavement, and we also introduced the some graphs to do the calculation about the stress and strain at different locations in the flexible pavement. And we stopped at the introduction about the the example. In the lecture, we in this example we assume that there's an flexible pavement, and the pavement is homogeneous. And we also know that there's a load from the two tiles applied to the pavement. The tile pressure is 50 psi, and the radius, the diameters of the contact area, which would be the contact area of the tire and the pavement, is 10 inches. And the elastic modulus of the pavement is set as 10,000 psi, and the Poisson's ratio is 0.5. We want to find out the vertical stress, strain, and deflection at the point A. Point A is just behind the center line of the left tire, and the thickness of the depth of the point A is 10 inches. With this information, we can then estimate the vertical stress, strain, and deflection. So let's see how we can find out the this information. I'm gonna share my go to the presentation mode. So first of all, we will need to collect all the information that we have from the example. We know the information of the modulus of elasticity for the pavement structure, which is 10,000 psi. So the that is capital E, and this is what we are provided. E equal to 10,000, and we have the Poisson's ratio V equal to 0.5, and the other thing we are provided is the it's the radius of the diameters of the contact area. So we have the diameter is 10 inches, which means that the radius of the contact area A is 5 inches. Also, we know the spacing between these two tiles is 20 inches. And for the load applied from the tire is Q, the contact pressure, is set as 50 psi for both tires. And we also know the thickness of the point A, that is 10 inches. So with that, we can then quickly get the information about the ratio between the thickness, the depth of the point A, and the radius. So Z is 10, and the radius is 5, which will give you the value as 2. And for the left tire, so this is the left tire, as A is directly behind the center line of the left tire, so the distance of point A to the center line of the left tire, that is R over A, should be 0. Here r is 0. R is the distance from point A to the center line. And with this information, we can then find out the value of sigma z divided by q. So from the figures that we provided in the previous pages. So first of all, we know the value of r z over a. It's z over a is 2. The value of the r, the ratio r over a is 0. Then let's go back to the figure previously for the in this figure, we know the z over a is 2 and r over a is 0. So with that, we can find out the line, which would be the line, the outside line. This one represents r over a equal to 0. And we also know the value of z over a is 2. So this is the point we want to select. By choosing the value of 2, z over a equal to 2, you can find out the value of sigma z over q as 0.28. This will be some, so it's a 28%. So it's which is a 0.28. And similarly, you can find out the value of sigma z over q. That will be the second graph. For the sigma r over q, the radiant stress with respect to the contact pressure. We have the similar selections for z over a equal to 2, the r over a equal to 0 for the outside line. And this one will give you the value about sigma r over q as you need to carefully choose the line. This is the line we're going to choose. And that will be the point. So the value is around 1.6%. So this is a 0.016 for sigma r over q. And similarly, you can go to find out the value of sigma t over q. The value you get is still it's also around 0.016. And you can also find out the parameters with respect to the deflection. So for that, you can get the value of f equals to 0.68. So with that, we have all the necessary information to calculate the vertical stress. So we have sigma z over q equal to 0.28, sigma r over q equal to 0.016, sigma t over q equal to 0.016, and f equal to 0.68. And with the first equation, you can calculate the value of sigma z as 0.28 times q. Q is 50 psi. So this one give you the value as 14.0 psi. And then you can get the value of sigma r as 0.8 psi. And sigma t is also 0.8 psi. So this is only the information, only the impact from the left tire. We also need to analyze the stress from the right tire, which will have the distance from point A to the center line about 20 inches. And in the second situation, for the right tire, For the right tire, we have R equal to 20 inches, and Z is the depth is still 10 inches. So with that, you get a Z over A still as 2, and R over A as 4. And then you can follow the same procedure to find out the value of sigma Z over Q as 0.0076, sigma R over Q equal to 0.026, sigma T over Q equal to approximately 0. It's a very small value. And then you get a sigma Z. The vertical stress is a 0.38 psi, and sigma R is a 1.3 psi, and sigma T is 0. And the problem wants us to find out the value of the vertical stress. So for the point A, you need to find out the combined vertical stress from the left tire plus the right tire. So we have the total vertical stress, sigma Z, as the one from the left tire, 14.0, plus the one from the right tire, that is 0.38. So we get the value as 14.38 psi. So this is the vertical stress for the point A, and you can see that this one is mainly of the vertical stress is mainly determined by the left tire, and it means that the distance of the point to the center line of the tire is very important. It will dominate your values of the vertical stress. And similarly, you can find out the radiant stress, which is 0.8 plus 1.3. It's a 2.1 psi. It's a very small value. And the tangential stress is a 0.8 plus 0. It's just 0.8 psi. And for the vertical strain, we need to recall the stress-strain relationship. The vertical strain epsilon Z will equal to 1 divided by the capital E elastic modulus times sigma Z plus minus mu minus V times sigma R plus sigma T. And we know the value of sigma Z, we know the value of capital E, and also the Poisson's ratio. This is 1 over 10,000 times 14.38 minus 0.5 times 2.1 plus 0.8. And you get the value of the vertical strain as 0.00129. So this is a small strain at point A. And for the vertical deflection, as we have already obtained the value of F, the F from the left tire, or here I forgot to show the value of the F from the right tire. Capital F can also be obtained as 0.21. Then from the two tires, the F value is 0.68 plus 0.21, that is 0.89. And we know that the deflection omega equal to Q times A divided by E times F. So Q is 50, A is 5 inches, and capital E is 10,000. F is 0.89. It will give you the final solution about the deflection as 0.022 inches. So we're going to observe about 0.022 inches deflection at point A. So this is the way for you to calculate the stress strain and the deflections at any point behind a load applied to the pavement, a flexible pavement. So that's all about the first part analysis of the stress strain analysis of the flexible pavement. Do you have any questions? Okay. If no, then I will gonna switch to the next one. We have some other methods to further analysis the stress and strain for the flexible pavement with more complicated, more realistic settings about the pavement structures and also the properties of the materials. So that will goes to node 20. So in the node 20, we will continue the introduction about the stress and strain analysis of the flexible pavement, but here we're going to focus on the multi-layer elastic theory. And actually in the analysis of the flexible in the analysis of the stress and strain of the pavement, the challenges like the materials, at most of the situation, the property of the materials will not be constant. Instead, it's changing at different locations of the pavement and also at different depths. And also this kind of property, these changes is not linear. And in general, most of the time they will be non-linear. So this kind of features increase the difficulty for us to find out the true mechanics of the pavement under different loadings. And also we need to think about the impact of the environments and the traffic load. Their impact is not as simple as what we modeled. The figure here shows the one important soil material property, the elastic modulus, under different depths of the pavement, as well as the radial distance, which will be the distance to the center line. And you can see that the modulus of elasticity is changing dramatically when the radial distance is below, it's less than 30 inches. So this is 30 inches. And also they have very significant difference about the modulus elasticity at different depths, as what you can see about the different colors. So this all increased the difficulty for us to find out the realistic stress and strain for the pavement. So we also have another figures observed from the reality. We can see that the elastic modulus is actually changing with respect to the depth of the pavement structure. So this nonlinear relationship about the elastic modulus further increased the difficulty for us to do the analysis. But for this class, we want to start with some simple case. Instead of assuming realistic properties of the modulus elasticity, we will try to start with a simple case by discretize the pavement structure into different layers. And in each layer, we assume that, or in in each asphalt layer, base layer or subbase layer, we assume that the property is homogeneous. And this one can help us to simplify the analysis a lot. Let's start with the simplest situation. We assume that there isn't any layers for the pavement structure, which were just like the unpaved road. Then the properties of the subgrade will be the same. We have constant elastic modulus, and with that, the stress in this kind of homogeneous ground could be evaluated based on the Boussinesq solution. This is one of the most straightforward method to estimate the stress and strain in the in this simplified situation. So then let's go to see how we're gonna use the Boussinesq solution to estimate the stress and strain. So so this figure shows the situation, shows one specific situation when we have the stress generated by a point load. So the load is only applied at one point instead of applied in the contact area. And if we assume that the applied load is a capital P, and for any points in the pavement structure, if for the point A, if the depth is Z here is the depth of the depth of the point, and R here is the direct distance from the point of the load to the point A, and we can actually find out the location of point A based on the its coordinates, assuming that we have the 3D rectangular coordinates. Then the location of point A could be assumed as x, y, and z. Z is depth, x is the distance to the y-axis, and y is the distance to the x-axis. So this is the location of point A, and another thing like it's the variable r. R is the distance from A to the center line of the load. So which would be the perpendicular distance to the z-axis. And if we are provided with all this information, you can then calculate the vertical stress at point A with this formula. Where sigma z is 3 times p divided by 2 pi times z square. Z is the depth of the point A, times 1 divided by 1 plus r over z. R is the distance to the center line, to the power of 5 divided by 2. And this can be further simplified as 3 times p times z to the power 3 divided by 2 pi r to the power of 5. And r is the distance from A to the loading point. And we can always use this information to find out the stress, the vertical stress at any point in the pavement structure. But you have to know that this one only applies to the homogeneous ground. In reality, you can assume the unpaved road or some very thick asphalt concrete pavement will have the homogeneous ground. And the other thing that we want to specify is about the stress under the circular contact area, instead of point load. assuming that the contact area, if the contact area is in a circle, and if we are provided with the radius of the contact area here, R0 is the radius of the contact area. Then we can calculate the vertical stress under the center line. So remember that this is the vertical stress under the center line of the with the depth of z. So z is depth. And this equation shows the value, shows the formula to calculate the vertical stress under the center line, and it also from the Boussinesq solution. So this would be the two different situations: the vertical stress with the point load, the vertical stress with the load under the circular area. And in this equation, Q would be the contact pressure or the load. Contact pressure or the loading pressure. So that will be the Boussinesq solution, and we also have another simplified method, which is called a 2-to-1 method, to find out the approximate stress under different depths of the pavement structure. And this method assumes that the stress is a uniform distributed at a different at one fixed depth, and the areas covered by the affected by the load will be similar to the contact area if the contact area is the square or the rectangle. Then the area affected by the load at the depth of z is also in the square. It's also in the rectangle. And for the but definitely the area at the depth of z will be much larger than the one at the surface, and the scale of the affected area at the depth of z is determined by the 2-to-1 rule. So the slope of the affected area with respect to the contact area is 2-to-1. So you have the vertical distance of 2 and with the horizontal distance of 1, which means that you increase the depth of 2 feet, then the width will increase about 1 feet on each side. So what you're going to observe is like with the increase of the with the depth of z, you will observe the contact area will be increased from the top at the surface b by l, but at the depth of z, that will be b plus z by l plus z. And with that, you can find out the stress at the depth of z for any point in the affected area as q times b times l, which would be the area, the contact area at the surface, divided by the affected area at the depth of z. And this also applies to the case with the circular contact area, assuming that the at the surface the contact area is in a circle with the radius of r, and then the contact area is pi times a. It's pi times a square. But at the depth of the z, the radius will increase to a plus z divided by 2 with the depth of z. and then the area, the affected area at the depth of z would be pi times a plus z divided by 2 square. And then you can go to check the stress at the depth of the z as q times a square divided by a plus z divided by 2 square. So this one is actually q times pi a square divided by pi a plus z divided by 2 square. And you can remove z on both at the top and the bottom. So this is one approximation. It assumes that the stress at the fixed depths will be constant, and the affected area at the one depth is dominated by the 2-to-1 rule. So that's the another method that can be applied for us to estimate the vertical stress. And we can also use the empirical data to further identify the vertical stress at any depth, at any location behind the pavement structure. And this is the figure we're going to use in the previous, we applied in the previous lecture. So we have the, assuming that we have a circular contact area with the radius of A and a contact pressure of Q, and you know the distance to the center line as R, the depth of Z, then you can find out the vertical stress from this graph, which will tell you the ratio between sigma Z and Q for the horizontal axis. We have already introduced this one from the previous lecture. You can also find out a way to calculate the radiant stress, the tangential stress, and the shear stress. So this is only applied for the homogeneous ground. And for the vertical deflection, we have another equation to calculate the vertical deflection just behind the center line, assuming that we assuming that there's a circular contact area with the radius of A and the contact pressure of the Q. Then we can calculate the vertical deflection at any depth, say that the depth of Z. This equation shows the formula to calculate the vertical deflection at the point A with the depth of Z, and it's determined by the modulus, the Poisson's ratio, mu, the elastic modulus, the radius of the contact area, and also the depth of the point. And if we go to check the details of this formula, you can see that if mu equal to 0.5, the Poisson's ratio is 0.5. This term will be 0. And then you can get a simplified expression about the vertical deflection. And this one is the simplified formula. You have the deflection W equal to 1 plus mu times QA divided by E times F. F is the deflection factor. And you can also get the value of F as 3/2 times A divided by A squared plus square root of A squared plus Z squared. And obviously, if you set Z equal to 0, if we set Z equal to 0 for this equation, you can find out the maximum value. You can find out the maximum value of F, and the maximum value of F would be 1.5, and this will give you the maximum value of the vertical deflection behind along the center line of the contact area. And in addition, you can find out the if z equal to 0, you can find out the maximum deflection as this function, that is 2 times 1 minus mu square times q times a divided by e. So this is the theoretical model for you to estimate the deflection at any point along the center line with any depth. And we can also use, as we showed in the previous lecture, we can also use the empirical information from the graph to find out the vertical deflection for any points, not only the points behind in the center line, but also the points in the other in other location with certain distance to the center line. So this is the one as we have already introduced in the previous lecture, and also you can find out that at mu equal to 0.5, at z equal to 0, you can get the maximum value of Fm at 1.5, which would be the highest value you can observe from this graph. So this is about the deflection, the vertical deflection, and for the other points, we can also have the theoretical solutions in addition to the to this graph. With the theoretical solutions, the formula is a little bit complicated. For the point A, with the depth of z, with the distance to the center line of r, you can find out the vertical deflection determined by this equation, and the in this equation you have the parameters of g and the parameters of capital P and R, which will all be related to the properties of the material, the locations of the point, and also the contact, the load applied in the contact area. And now let's go to see one simple example for the calculation of the vertical stress and the deflection at point A with the Boussinesq solution. And in this problem, we have a single tile applied to the pavement structure, and we know the contact area is has a radius of 5 inches with a diameter of 10 inches. So we have the radius is 10 divided by 2. That is 5 inches. And also we know the load Q is 50 psi, and the the modulus of elasticity is 10,000. Poisson's ratio is 0.3, and we are trying to find out the vertical stress and deflection at point A. So A is just behind the contact area, the center line of the contact area. The depth is 10 inches. And also we know that as A is along the center line, so we have R equal to 0. And with that, we can then calculate the vertical stress. For the vertical stress, we have sigma equal to Q times 1 minus 1 divided by 1 plus A divided by Z square 3/3 3/2, and you know the value of Q. You can also know the ratio between A and Z. With that, you can find out the vertical stress as of 14.2 psi. So this is about the vertical stress. And then for the vertical deflection, W equal to the equation I showed in the previous page, 1 plus mu times QA. Mu is 0.3, and Q is 50, and times A divided by A squared plus Z squared square root plus 1 minus 2 mu divided by A times square root of A squared plus Z squared minus Z. And you can apply all the values from the assumption, and this will give you a deflection as 0.0176. So that's the way for you to apply the Boussinesq solution for the calculation of the vertical stress and deflections at point A. You can, in order to do these calculations, you need to know exactly where the location is. For this example, A is behind the center line, and the depth is 10 inches. You also need to know the ground is homogeneous. It's homogeneous with the elastic modulus of 10,000 psi, the Poisson's ratio of 0.3. And also you have to know the contact area and the pressure. In this example, 50 psi, and the diameter is 10 inches. And then you have all the information for you to do the calculation to find out the vertical stress and the strain, the deflection. So I think I will stop here and reserve the rest 5 minutes for the in-class questions. Let me try to make the questions available for you on Avenue to Learn, and you can start to work on the question. Okay, so for now, I think it's available for you to view. You can access to Avenue to Learn to work on the simple question. This one is related to the estimations of the traffic loadings and volumes. You can refer to the notes, note 18 and 19, 17 and 18 to find out the formula and calculate the values. Okay, so we can start work now, and I will stop recording the video and wait for any potential questions.